Well, guys, today I want to talk about one of the problems that I've seen when I took discrete mathematics. I kind of like this problem. It's like classic in it, and it's probably a basic one, but I kind of like it. Like, I don't know how to describe it. When I first saw this exercise question, I could not actually do it, and to me it seems cool that we're just one ask away. I just asked one guy, and he told me exactly the key to solving the problem. You might be wondering, what kind of problem is that? Well, okay, allow me to show you. Suppose we have a grid. Wait, hold on. Suppose we have a grid like this. Um, I'm just going to demonstrate this with this kind of dimensions. It's actually the grid actually has a fixed dimension, more like a specified dimension. Namely, it has to be 2 to the power of n times 2 to the power of n. So you need to have 2 to the power of n tiles across, and then 2 to the power of n tiles down. So in this case, we pick n equal 2. But then we have to remove one of the tiles here. So I'm just going to pick one at random, for instance, here. Just say it's removed, it's punctured, it's like drill a hole in a shape so that this thing is unusable. Now, can we try to cover this grid with one of its tiles removed with this shape? So I'm going to call this the L shape. Can we try to do it? I can give you like a second to think about this. You can pause the video if you want to find a solution to it. All right, so let me just try it out. We put the L shape here. Maybe we can put the L shape here. Then here. Oh, look, we can actually cover it. So for this particular shape and for this particular placement of the hole, we can cover the entire grid with only L shapes. I want you to think, is it possible to do this for every grid of size 2n, or 2 to the power of n, times 2 to the power of n? And by the way, yes, I'm going to say the words 2 to the power of n a lot of times. It's not 2n, it's 2 to the power of n. And yes, it's a lengthy one. With these L shapes. So our problem statement is proof or show that 2 to the power of n times 2 to the power of n board with one of its tiles removed can be covered by L shapes. Right. Might be wondering how this shows up in discrete mathematics. When I saw this problem the first time as well, I was kind of confused because there's no way you can kind of mathematize it. It doesn't, if that's the word that even makes sense. Basically, how do you even transform this into a mathematical statement or a mathematical problem? Because when I first saw it, I was like, oh, that's just going to be trial and error. And then with the amount of generality involved, because you want the grid to have this size, that would be kind of difficult. Because how do you even quantify things when the grid has like 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and like, how do you do that in general? Well, it turns out the trick, not the trick actually, is it? The general method to solving this is something in mathematical induction. here. How do you even apply mathematical induction to this? Well, it's not immediately obvious, but in case you don't know, well, actually, I have to explain to you first what mathematical induction is. So there are two types of mathematical induction. We've got the weak induction and strong induction. So I'm not gonna go too deep into what mathematical induction is, though. It's a way to prove statements that involve something along the lines of uh, an integer. So here we see that our statement goes like this, and it depends on n. It depends on n. We want to prove that for every n uh, equal to or greater than 1, you can solve the statement is true. And mathematical induction is one of the general strategies that you can employ in order to prove it. I know if you read like Introduction to Proofs kind of book, you'll see them describe mathematical inductions as trying to what is it? As trying to place a domino, not place. I mean, as trying to knock one domino and then have all the dominoes in front of it fall over. So if it just goes like this, for instance, it will knock this domino, and then this domino will knock this domino, and then this thing to knock this domino, and so on and so forth. And that's the kind of illustration that those books usually give you. Well, what does that even mean? So you can see why if you take a look at the algorithm for mathematical induction, or rather the steps to do it. So a typical mathematical induction proof has two main steps. One is the base step. We want to prove, in the base step, we have to prove that it is true for the smallest case, as in the case with the smallest n. Generally, it can be n equals 1, but if it's not, then it's just the smallest n that it applies to. Prove that P1 is true. What is P1? P1 is a shorthand for the statement we want to prove. So here, you wouldn't want me to recite this statement over and over again. So we can just give a shorthand to it. So let's just say it's Pn. So here, one of the things that changes throughout when you one of the things that change in the entire statement as you move n in the natural numbers is that the board gets bigger, basically. Look at this. And now we have to prove it first for n equals 1. The second step is the inductive step. The inductive step will differ based on what kind of induction we're trying to use. For the weak induction, we have to assume that it is true for n equals k minus 1, with k being in the natural number. So assume that k minus 1 is true. From here, we try to use the assumption that this is true to prove that pk minus 1 in implies the truth of pk. So so in this case, we will have to actually no, I'm not gonna show you exactly how to do it right now, but we're gonna move on first. So it's the other type is strong induction. In this case, we assume not only pk minus 1 is true, but also pk minus 2, pk minus 3, all the way to p2. So we assume that it holds for every k in the natural numbers before before k. No, I mean like it holds for every natural number for k. We have to use the truth, the assumed truth of all these statements to prove pk. All right. Now that we know the two kinds of induction, let's move on to prove the statement. Right. So first of all, the first thing I have to do is the base step. Remember in the base step we have to prove for the truth of P1. So that means we have to prove that it holds for n equals 1. So an n equals 1 variant of the statement means you can cover a grid like this to a 2 by 2 grid with one of its tiles removed. I'm going to pick one at random here. So here we have to show that every 2 by 2 grid with one of its tiles removed can be covered with an L shape. Here the option is the solution is obvious. You can just put an L shape here. Now, if I were to say move the thing, if I were to move the remove tile here instead, strategy is the same. You just put an L shape in an easy way, in an easy to see way here. And there are 4 configurations. You can see why there are 4 configurations, and they're all obvious as well. So in this case, yes, we can cover this kind of grid with one of its tiles removed with an L shape. So we conclude that P1 is true. The second step is the inductive step. And this is where we have to generalize. So how do you draw a general 2 to the power of n times 2 to the power of n board? You can't. But I'm going to show you with a large enough board that it makes sense to kind of see where it's going. So the next largest so the next largest board after 2 by 2 and 4 by 4 is the 8 by 8. I'm gonna have to see how to draw it here. If I draw here, oh wait, okay, right. And then we have to pick one tile at random. That's gonna be here, for instance. And remember, we're actually trying to prove things with a general case, not just for n equals 3, for in this case. I'm just going to show you how it works. So I'm going to use something viable enough to show the board is large enough. So here we have a 2 to the power of n times 2 to the power of n. Now, this is supposed to be the case where we use mathematical induction, but it doesn't seem clear what we're trying to achieve if we're just using this at a stage. I'm going to give you 2 seconds to think about how to proceed from here. And this is exactly where where I was stuck when I did it the first time. All right, can you see it? Can you see the way forward? Right. Remember that in the methods, in the algorithm for the induction, the mathematical induction, we have to assume some variant of the truth of bk minus 1, as in the truth of something before k. Actually, I have to make a little bit of correction here. And this isn't actually 2 to the power of n, just for the sake of like making it easy for you to follow. This is not 2 to the power of n. It's supposed to be 2 to the power of k. Now, we want to define a way to make 2 to the power of k minus 1 show up. How do you do that? Okay. Now, notice that 2 to the power of k over 2 divided by 2 is 2 to the power of k minus 1. All right. What does this have to do with the board? Well, it turns out you can divide the board. You can split the board into 2 here, for instance. Not for instance. That's the only way you can get 2 to the power of k. You see, if you split the board into 2 in this way, you have 2 to the power of k minus 1 tiles here. And then the other one has 2 to the power of k minus 1 tile as well. But we're not done yet. We can do it in the other direction as well, perpendicular here. So we have 2 to the power of k minus 1 showing up. Now notice that we have divided the board into 4 different smaller boards. And each smaller board has dimensions 2 to the power of k minus 1 times 2 to the power of k minus 1. And notice that each time you have something removed, if each time you have a tile removed, it will always belong into one of these 4 smaller boards. All right. Now, I'll give you 2 seconds to think how to move forward from this one. All right. So now you might be wondering, okay, you can make 2 to the power of k minus 1 show up. So that means there must be mathematical induction needs to have to be it has to show up here at some point. And yeah, this is exactly where we start. So remember that in the mathematical induction, we have to assume the truth of we have to assume the truth of the statement for n equals k minus 1. So what we're trying to assume here is that we can cover a smaller board with dimensions 2 to the power of k minus 1 times 2 to the power of k minus 1 with L shapes. So assume that we can cover this. But notice that the other 3 boards are 2 to the power of k minus 1 exactly. Sorry, 2 to the power of k minus 1 times 2 to the power of k minus 1 tiles exactly. While this particular smaller board has one of its tiles removed. So how do you proceed from here? Well, you place you place an L shape in this way. Why? Notice that in each of the 3 boards not used before, there's 1 tile removed from the game at least. It's not actually removed, it's rather unusable because we've already covered them like this. So now we've got 4 boards with 2 to the power of k minus 1 times 2 to the power of k minus 1 tiles, but with one of its tiles removed. But notice that this is part of the induction hypothesis. That means we just assumed that this smaller board can be covered. So that means this smaller board should be able to be covered, this smaller board should be coverable, whatever. And you can cover this one as well. In what way? Well, it doesn't show you how, it only shows you that you can. That's the part of mathematical induction. But yeah, basically that's the general strategy of doing this. Because of this, I'm just going to skip right to uh, the main result. Because of the induction hypothesis, we've shown that pk minus 1 implies pk, and this is exactly what we want to prove. Since we have proven the inductive step, that means the statement Pn is true by induction. Nice. And yeah, that's all for me. I don't know if I'll ever do more of this. Uh, I'm a consultant with very little free time, but sometimes I kind of just like to go back to my old math major days and explain to you mathematics. In fact, I've been shown this to my coworkers. I wonder if they understand. They probably won't. But yeah, see you guys next time.